This is a section in which we're going to start counting, so let's start here with some notation. Suppose I have a set S, and in this set S is A, B, C, D. Now I'm going to use this notation here, a lowercase n, parentheses S, and that's going to mean this. This is going to mean the number of elements in set S. So in our case, we would write this. This would be 4. Now I want to start counting elements in combinations of sets. So suppose that we have this set here, S. We got 4 elements at S, right? So we can even note that. The number in S is 4. And then we've got another set T, and the number of elements in T is what? 3, 4, 5. Now let's take the union of these two sets. So S union T, what are we going to do here? We're going to take everything out of S, put it in here, and everything out of T and put it in here, and just like dump them all together. So we're going to have what? A, B, C, D, E, F, G, giving us that the number of elements in S union T is equal to 7. What I'd like to have here is a formula that counts the number of elements and the union of these two sets, and involved in the formula are the individual counts, like right here. Now if we just wrote this, what if we just wrote this? The number in S plus the number in T. This is not going to work because I'll do these counts. In S union T we got 7. In S we had 4. In T we had 5. So far I've got 7 equals 9. Well, what I need to do here is to get back to 7, I need to subtract 2. But I have to account for that 2. Where does that 2 come from? Now look what happens when we make these counts. I'm up here at the top right. The number of elements in S is 4. The number in T is 5. But when I tossed them all into this big collection together, what happened? Well, the B got counted here and it got counted here. And what else got counted? The D got counted here and it got counted here. So B was common to both, D was common to both. That happens to be the intersection of those two sets. So that 2 is accounted for here. I'm going to subtract off the number in the intersection of those two sets. So here's the formula that we're looking for. This is one of the fundamental counting principles. So a quick direct example is this. What if I know that the number in A is equal to 12, the number in set B is equal to 10, and when I intersect them, A intersect B, I get 5. Now from this, can you find the number of elements in A union B? Sure, we have a formula for this. Here's how it goes. I'll do it down here at the bottom. Number in A union B is equal to, all right, you take the individuals, the number in A plus the number in B minus the number in the intersection. And what do we get here? Number in A is 12 plus the number in B is 10 minus the number in the intersection, which is 5. So we get 22 minus 5 is 17. All right, so there's 17 individual elements in the union of those two sets. Now a case that often comes up in probability is this. Suppose you have two sets and you intersect them, and that comes out to be empty. So there's nothing in common with these two sets. So you'd have a situation like this. Now this is called a Venn diagram. What I'm going to do is I'm going to draw each set, but there's no intersection. Right, so I'll just draw them so they're completely separated. This is set S, this is set T. Now, if there's nothing in the intersection, then when I count this, the number in S intersect T, that would be like counting the number of elements in the empty set, which is 0. So when I use my formula for counting the number of elements in the union, which is the number in the union is the number in S plus the number in T minus the number in the intersection of S and T, I get this. The number in S plus the number in T minus 0. And minus 0, I don't need to write that. So this is just going to be the number in S plus the number in T. And I'll finish it off down here, the number in S union T. So this is a formula that you can use when S and T have nothing in common. And I'll just make a statement up here, back up here up at the top. Okay, I'm back up here at the top. If this is the case for two sets, then we say this. S and T are what we call mutually exclusive. And you might think of that as this. If one occurs, the other cannot. So one of them occurring excludes the occurrence of the other. So like I'm saying this, if I've got something here in S, it cannot possibly be in T at the same time.